Okay, first of all, good morning, everyone. Um, for today's lecture, I would like to continue and finish off the chapter 9, and hopefully I can do that at least the primary content I will finish off, okay, for the chapter 9, and then for some additional resources, practice, I would like to try to add one additional video, okay, for you. And also, I have attached the link for your quiz since yesterday, so you could check the model, check the weeks. Okay, uh, I'm putting the link on week May 30th. Okay, so it's supposed to be at the second from the bottom. Okay. Okay. That will be the quiz chapter 8. The deadline is June 2nd. The deadline is June 2nd. But I think I will extend a little bit the deadline. Okay. Now I think we can move to our notes. Okay, now this is the last discussion that we have. So we have at least two methods. Okay, two methods for some cases in this reactive process. So the first case is if we have given the heat of reaction, which means if we have the heat of reactions given in the information, then we are going to have, I think, much more simplified calculations because we have known already the heat of reaction. The second method is we call the heat of formations, which means that we are not sure what is the heat of reaction, that we need to break down, or we need to make out ourselves, okay, the heat of reactions. And how do we make it? We are going to use some sort of listings from the table. Okay, so we have a heat of formation, and we are going to as in the stoichiometric process, we are going to construct equations, and then based on the informations, and we are going to have to utilize the heat of formations to find the heat of reaction. And that basically that is these two methods that we are looking at. Okay. Now to start off, okay, this today's lecture. To start off today's lecture, we are going to look on several examples. And I think if you have the text, we can also look out on your textbook what we have. Okay. So first is the let me write in the new page. First is this, okay? Energy balance about an ammonia oxidizer. So we have given the heat of reactions. Okay, now this is heat of reactions, right? This is heat of reactions. We are given the standard heat of reactions for the ammonia. Okay, we are given this equation, and then 100 mole per second, and 200 mole oxygen per second. They are going to be fed into the reactor. Okay, and the ammonia is all ammonia consumed. The product gas emerge at this 300 degrees Celsius, and calculate the rate at which heat must be transferred. Okay, and it's asking transfer to the reactor or from the reactor, and we need to assume that this operation is operate at 1 atmosphere, and this is, I think, most of the case in chapter 9. We will have a constant pressure. Can usually just take 1 atmosphere. Okay, so you have any questions related to the heat of reaction? Usually we are going to have a constant pressure. Okay, so you don't need to consider the pressure as variable. Okay. Now, to start off these questions, we are going to make a diagram as usual. Okay, this is, I think, pretty much usual, and label all the components. Right, so the ammonia, oxygen, 100 mole, 200 mole, as mentioned in given informations, and then we are having because we know that the reaction is giving this NO and water, we are going to have gas. Okay, at the output, okay, and we have the oxygens that is still in so the oxygen will consume the ammonia will consume completely, and they will still, there are several molecules of oxygens that is left in the system, okay. And then after we have this the diagram, the next thing we can do is of course, because we know this is heat of reaction, we are going to the heat of reactions method, and then we are going to choose the reference state. So choosing reference state, and usually we are going to just choose, because it's mentioned as 25 degrees Celsius and 1 atmosphere, so we are going to choose the T 25 degrees Celsius and pressure is 1 atmosphere. I think that's the very obvious choice for us. And after that, we're going to put into the table. Okay. So all the substance that we have, from the ammonia, oxygen, NO, water, oxygen, we are writing all the substance, all the moles, including the enthalpy that we are going to evaluate. And of course, for our case, we are going to have 0 for ammonia and oxygen, because that is our reference state, right? Okay. And then the rest we name as H1, H2, H3, and we are going to observe H1, H2, H3. Okay. So the unknown we are going to evaluate through either table or mostly table. Okay, mostly table. For the oxygen, for the H1, we are going to look on the table B8 because of the conditions itself. It's 300 degrees Celsius, right? 300 degrees Celsius. Table B8, we can get for several gas, and we can get from table B8. So for the oxygen, at 300 degrees Celsius, this will be 8 kilojoule per mole. So 8.4. And then for the H2, since this is NO is not in the table B8, so we could get from the table B2. Okay, so we are going to have the table B2. So from 25 to 300 degrees Celsius, Cp Dt. Okay. And find the Cp through the table B2. Calculate the integrations. Okay, you can just type in on your calculator, and then this will result in 8.4553 kilojoule per mole. And then H3 is the water. I think water is also gases that is on table B8, so you could just look at the table B8. So you could write H3 is going to be 9.57. Okay. After all this enthalpy, the next thing we are going to have is the extent of reactions. Let's say this is the for the ammonia. The stoichiometric of ammonia is, what is the ammonia? Is 4. Okay, so the molar flow is 100, right? And then the mole per second, and the stoichiometric is 4. It's supposed to be 25 mole per second. This is the extent of reaction. And why we need to look for extent of reaction? Because we are going to find the delta H. That is depends on the extent of reactions. Multiply with the delta HR, and then plus all the things that we find here, the enthalpy. Okay, so we need to So what's the difference between the chapter 8 and chapter 9? Basically, the chapter 8 we are talking here, right? This is chapter 8 mostly. Okay, we find it from the table, we put into the calculation and we find the delta H, right? Or we could also say it's chapter 7 also. But chapter 7 is mostly simplified, right? And chapter 8 we have several types of enthalpy, right? We get from table B2, B8, B11, etc. Okay? Now chapter 9 is actually adding this, okay? Adding the heat of reaction. Okay, that's the difference. Because we are having some reactive process, so we are having some why we have the extent of reaction, because the whole process that is involving the oxidations, okay, or some case it's combustion. This will have another. It takes another heat. Okay? It takes another heat that you need to add it into the whole system for your delta H. Okay? Now, nevertheless, let's just take a look at this delta H. Okay? This is 25, and then the heat of reaction is 900, right? And then I think we just take this moles, okay, and then multiply with the H, and then I think you can take it to some value, and it's supposed to be equal to 19,700 kilojoule per second. And from here, we could say that the heat flow is equal or approximately delta H, because I think they are not mentioning other parts that is appear in this system. So you could just take these approximations, and we know that this is kilojoule per second, or we could directly write the kilowatt. Okay, so the important thing is choosing reference state, take out to the reference table, and find each enthalpy. Find each enthalpy and then put into the whole enthalpy system. Okay. If you have a multiple reactions, okay, and you have it's supposed that you have two calculations on the extent of reaction, then to avoid any complications, you can choose just as the elemental species as reference to simplify the process. Okay, so maybe let me write here, if more than one reaction occurs, choose the elemental species as reference to avoid complications. Okay, if not, for example, if you have two reactions, then you have two extent of reactions, right? And then the process can be a little bit complicated. Another point of view for our case is let me give you an example on the adiabatic reactor. Okay, so this is a process with unknown outlet conditions. Let's say we have the case on adiabatic reactors. Okay, let's say we have the hydrogenations of ethanol to form the acetaldehyde. This is carried out on adiabatic reactor, continuous adiabatic reactor. Ethanol vapor is fed through the reactor at this 400 degrees Celsius, and it's converted in a 30% conversions. Okay? Calculate the product temperature. Okay. So the temperature, we call the temperature at this case is this temperature, adiabatic temperature. Okay, just to note the terms. Okay. And then choose the reference. Choose reference. And since it's better just to choose reference at the room temperature and 1 atmosphere, I think we can just go to mentioning in the table. So we put the table. So ethanol 100 mole, right? 100 mole. So let's say we take the basis of 100 mole of the ethanol, so 100 mole, and it's become 30%, okay, 30% product, it's 70 mole for ethanol, 30 mole of the acetaldehyde, okay? And then the 30 mole for the hydrogen from the stoichiometric, okay, from the stoichiometric. Okay, now we are writing all enthalpy, H1, H2, H3, and H4. Now first is we could work out on the extent of reactions. Okay, so first finding the extent of reactions. The mole of the acetaldehyde divided by the stoichiometric, because the input doesn't have the acetaldehyde, so we could just focus on the outside is 30 mole divide 1 stoichiometric coefficient, so it's just at 30 mole. Okay, and then we can write the whole adiabatic process in the reactor as the enthalpy, the extent of reactions, the standard heat of reactions, plus all the process here. Okay, and this is supposed to be equal to 0 because of adiabatic. Okay, heat will be 0. First is maybe looking on this heat of reactions, because we don't have information about the heat of reactions and we need to construct ourselves. So the standard heat of reactions we construct from the heat of formation. So the product minus the system. So product is 1, This is stoichiometric. The one is stoichiometric coefficient. So the product minus the reactor sorry, it should be ethanol. Okay, and then look on the table. Table B1 for the delta HF, right? The standard of heat formation. And you pick out the numbers and you get the standard heat of reactions is around 69.11 kilojoule per mole. Okay, I hope you don't mind I skip some numbering and some calculations. Okay, and then after at least we get the heat of reactions, lastly we are going to find the enthalpy each of this. Okay. So inlet enthalpy, the H1, we got it. I believe we could find the CP from the table B2 for the ethanol. CPDT using table B2, and eventually you will get the H1 is 33.79 kilojoule per mole. And similarly, table B2 is used for other as well. And also other sources that is not mentioning in the question, but in the I hope you can, if you have the books, you can read that. They are giving sources for CP if it doesn't have in the table. Okay, and then you can have for H2 it was given 4.958, and the T is written as the adiabatic temperature, so T80. Okay, and then actually from here, from H2, H3, and H4, it's also having the adiabatic equations, and you need to solve one by one to find the T adiabatic at the end. Okay, so you are going to involving this heat of reactions. Okay, and then so let me write through here. So heat of reactions we are going to put here. So the heat of reactions is 69.11, right? And this is 30 mole. And the rest is we have 70 mole H2 plus 30 mole of H4 minus 100 mole of H1, right? Now H2, H4, and H1. Oh, I forgot the H3. It's supposed to be here. So H2, H3, H4, and H1, they are having all with the T adiabatic, right? The adiabatic equation from here. Okay. So H2, H3, H4, they will have some component with T adiabatic. And since we know that this is going to be some number for this one, and the delta H is equal 0, we can solve for T, right? for T, and this T is our solutions. It seems a little bit complicated, especially when you are having this CP. Okay, but that is how you solve the problem. But I think in the questions in the exercise, most of the questions I think already been simplified. So I hope the computation is a little bit simpler. But nevertheless, let's just focus on the next sections, which is I think last sessions, the primary content. Okay, aside from the additional content such as the combustions, the ignition, right? The adiabatic temperature in the definitions, higher heating value. Okay. Okay. Let me go through at least this thermochemistry and the higher heating value and lower heating value. Okay. Okay, that's for the adiabatic reactor, finding the adiabatic temperature. Okay. Okay, let me move to the next one. The next one is the thermochemistry of solutions. So this is what we have. Okay. Let me check if we have. Okay. So the enthalpy change associated with the formation of a solution from the solid elements and the solvent at 25 degrees Celsius is called the standard heat of formation of the solutions, or we could just write delta HF solution, and it is equal to, so it has the solute, okay, it has the so we can write, this is the same, so this is the same with the chapter 8, the heat of solutions. Okay, heat of solutions. So for example, if you have the reactions for the HNO3 aqueous, and we know the R, and we have the calcium hydroxide, and we have also know the R is infinite, this is also infinite, plus 2H2O, the liquid. Okay, now the heat of reactions we can write down as using the heat of formation for the calcium nitrate plus 2 of water and then minus the 2 of the delta HF of H and O3 and minus the calcium hydroxide. And then if you look on the delta HF for each components, this will result in negative 114.2 kilojoule per mole. So it actually signifies that if a solution containing 2 moles of HNO3, okay, so if we have the 2 mole HNO3 and 50 mole of water, then this will be neutralized at 25 degrees Celsius with 1 mole of calcium hydroxide. So it dissolves in enough water so that the addition of more water is not going to change the enthalpy. Okay. Okay. There are some part on the neutralizations that you can actually look on the textbook. Well, what I want to look at another uh, definition is the higher heating value and lower heating value. Okay. I will emphasize this neutralization process on the other videos that I will prepare, and also some exercise for you. Okay. Let me just go to the some notes on the combustion, on the combustion process. Okay, let me give you this definition first. The heating value of combustible material is the negative of the standard heat of combustion. So this is the idea. First is the idea. So higher heating value, or the total heating value, or the gross heating value. So it's mentioning all the heating value, is a negative delta HC, the combustion, with water, liquid as a combustion product, and the lower heating value. This is based on when the water in the vapor, okay, as a product. Okay. Since the delta of the change in the combustion, the enthalpy combustion is always negative, the heating value is positive. Okay. So this is actually, if we look on the in the overview, the higher heating value is the lower heating value plus the some change in the heat, okay, for water at 25 degrees Celsius. And usually the heat of vaporization of water is around 0.13 kilojoule per mole. And if this is having a mix of substance for combustible substance, the heating value is going to be the separate, become some components. This is the heating value of IV component or combustible substance, and X is the mass fraction of fuel components. To apply this heating value is, for example, you have a gas. If I have, oh yeah, we have this. You have a gas that is contain 85% methane and 15% ethane by volume. The heat of combustion is given, so this is heat of combustion. Calculate a higher heating value of the natural gas. So first, we take the 1 mole fuel, okay, as our basis. This will give you 85% methane, which means 0.85 methane and 0.15 ethane. And we exchange to the gram through molecular weight. and we get the idea on the total mass is 18.1 gram. Okay, so we could find the fractions for methane. In 1 gram fuel. And fractions for the ethane, we could just take 1 minus 0.5. And this was at 0.249. Okay. Per 1 gram fuel. Now, then after we get these fractions, we are going to find the higher heating value is lower heating value plus and H2O heat vaporization of water. Okay. Then this will be giving you the the lower heating value is actually this. We have given the combustion, right? The negative, so negative, negative, so it's positive, right? So 802 kilojoule per mole plus uh, the mole is 2, right? 2 mole H2O per 1 mole CH4, right? From the stoichiometric reaction. And this is 44.013 kilojoule per mole of H2O. And we're going to multiply with 1 mole molecular weight, and this will be equal to 55.6 kilojoule per gram. And same thing we did with the higher heating value for the ethane. This will be lower heating value of the ethane. This will be 1428, becomes positive. And this is 3 moles, right? 3 moles of the H2O per 1 mole of ethane. And heat of vaporization of water. And 1 mole divided by 30 gram to 86. Yeah, the molecular weight. And then this will be the 52 kilojoule per gram. So we have each higher heating value, methane and ethane. And the total, okay, of the mixture, we are going to use the mass fractions for each component. So this is methane and this is ethane. And then you are multiplying all the mass fraction here with the higher heating value and plus the 2. Okay? And this will give you 54.7 kilojoule per gram. Okay, I think it's not really I hope the calculation is not really that taking some complicated process. Okay, and the rest of the sections, if I would like to let me just take into my PDF, okay, the book's PDF. Okay, so first of all, is we define this adiabatic flame temperature, right? The calculation we did in the previous calculations, that we find what we need to find the temperature. That temperature we can call the temperature of adiabatic flame temperature. It is the highest achievable temperature if the reactor is adiabatic. Okay, I think let me just show you some part of it. So the adiabatic flame temperature, okay. Yeah, this is similar what we did before, right? So we check the capacity, and later on, we are going to define this T as our T adiabatics, okay? So all becomes T adiabatic that we are going to find throughout some calculations. And because it's adiabatic, the heat that is going to be transferred is zero. So which means that you are able to find the temperature, right? And aside from that, there are some terms, and some terms that you are going to see. Okay. First is the flammability and ignition. So uh, first, we define the combustion. Okay, combustion defined as a rapid high temperature oxidation reactions. Okay, and I think you can just look at this. And since our finals will be an open notes, open books, and hopefully you can at least not really memorizing the terms, but try to understand what the context within the words. Okay, the context within the words. And also we have the ignitions. Okay, it can be described in this graph. Okay, the temperature of ignition. So you have so-called the ignition lag. So that is, there are some time, okay, some interval that when the mixture is going to ignite, reaching the temperature ignition, there is some moment that you will have like um, I'm not sure if you are familiar when there are some detonated, or maybe some nuclear, like you have like a bombing, okay? Before it goes to so like when you have like bomb like this, before it's blow, there's some slight of silent moment. Okay, that is the lag. Okay, before it's ignite, because the ignite is not just like in a slow motions, right? It's like really really quick. So before and after is just plus, right? It's having like boom. Okay, so that's the ignition lag. And then you also have we call the flammability limit. So you have it depends on the mixture of a fuel air mixture, whether you have the upper or rich flammability limit. So it's you have like a range within the combustion. Okay, and yeah, we can design the range for the explosive actually. And then we have the ignition temperature, flammability limits. We have also the uh, the flame. Okay, sometimes we can observe the color from the flame, right? And also we got something is we call the flashback. Okay? So the flame travels back through the tube toward the fuel source. Okay? Yeah. Okay, I think you can try to work out the reading. And here also important, the shock wave, okay, detonations. So when you are usually if in the visuals, this is the bomb, right? You have something like the wave. Like if you are maybe in nearby the some radius, okay, within the bombing, the ignitions, you'll feel like there are some shock wave like push you through, right? Okay. If you are, I'm not sure, maybe if you watch some movies, okay. And also, yeah, I think that is most of the last sections. It's actually going to be some terms, some definitions on flammability, ignitions, right? Flashback, and so on and so forth, and adiabatic flame temperature also. Right? So that is mostly the primary content on chapter 9. Okay? I will give you additional videos, okay, emphasizing some parts of chapter 9 that haven't been explained really in depth. But actually, it's on the examples on your textbook. If you want, you can read those too. And I will also add maybe 2 or 3 exercise from the chapter 9, and maybe a little bit on from chapter 8 to help you work out on the question. Okay, and don't forget to work out the quiz. Okay, work out the quiz chapter 8. Yeah. Any questions? Any questions before we end the lecture? Any questions first?
Yeah, yes, sir.
Yeah.
Sir, there was a question on the exam,
Mm-hmm.
on the last quiz. I just wanted to ask. It said that which of the following, please select which of the following applies. Energy can be transferred across which of the following system? It had closed system and open system,
Mm-hmm.
and for each closed system and open system, they varied in that both had steady state and unsteady state. So
Mm-hmm.
obviously, we know that energy is in the form of heat.
Mm-hmm.
So we know that it's only for isolated system where like no heat is transferred. So for
Mm-hmm.
me now, I was thinking to myself that it doesn't really matter if the transfer of heat is steady state or unsteady state, then the heat going across the system is still flowing, whether it's steady or not. And if it's open, it flows. And if it's closed, heat flows across the boundary. So it's not like it's mass. So I just wanted
Mm-hmm.
to ask for that question, all 4 answers applied, right?
Yes. Yes. Yes.
Okay.
Correct. Correct. Yeah. It's just like it's a trick question. Uh, like it's supposed to be like all system is happening. Okay. So it's just like a trick
Okay.
question. Okay. Uh, Jordy, you asked about what? So we don't do the quiz during, yeah. So we don't do the quiz during the class. So you just take the quiz like you did before on chapter 7. So you can do anytime before, I think before the second of June. Okay. So you can take times. Okay. Maybe you can prepare. My suggestion for you to help you to sometimes when you study, if you just rely on the books or notes that you have from maybe uh, previous or last year's courses, try to make out a new one. Okay, because I think it's on also one research suggests that when you write notes, you actually study. So when you write notes, you take notes, so you are making a new one. So it means that you are going to be able to visualize what you are writing. So I think it will be best to help you after you maybe read some part and then you think that, okay, I need to make some summary. I believe it's able to make a structure in your mind to get into what's the best way to practice. Okay, so I believe that is one one helpful suggestions that you can do. Make a new summary, and then maybe you can try to fill out 2 or 3 exercise in the different papers. Okay, but you need to make maybe one paper or 2 papers for each chapter. Maybe chapter 7 one paper, chapter 8 one paper, chapter 9 another paper. Make a summary. Okay, I think it will be helpful. So when you are doing the quiz, you have a more structured method to take out for each question. Okay? And then you will be more organized, I think. Okay. And yeah, try to check out the quiz, and we will see you later on the final exam. Okay, so final exam, we will have a WebEx, the same WebEx. I will announce later on when we are maybe a day before or 2 days before the exam, and some of the preparations that you need to make. And the exam itself, open notes, you can prepare any notes. If you want to use books, that's okay. But my suggestions, note, to help you to tackle like several questions at a time. Okay. And in the meantime, you can try to practice. Okay, if you have the textbook and practice, I will add at least one more additional video for chapter 9, including some exercise. Okay, probably the video will be on Wednesday. Probably. Okay, you can check later. Okay. If there's no
Thank you,
question,
sir.
yeah. If there's no other questions, we will have finished. So we finished the class. Okay.
So, sorry, no class on Thursday, right?
Yeah, no class on Thursday.
Bye-bye.
Okay. Okay, any questions? If you don't have, we can sum up our class. Okay. You're welcome, Rivaldo. Okay. Don't forget to check the quiz, okay?